So hello and welcome to this video where we are going to discuss a nice problem from the textbook Introduction to Electrodynamics by Griffiths, a very widely used and widely loved electrodynamics textbook for an introduction of the subject. So we are going to look at a problem from the very first chapter in which the author introduces the mathematical tools needed for the study of electrodynamics. So in this problem, we have to check the divergence theorem. We are given a particular vector field. So vector fields are of very central importance in electrodynamics because the electric field and the magnetic field are vector fields, and these two fields are the central points of study. The most important things that we study in this subject, electrodynamics. So all kinds of mathematics related to these vector fields is introduced in this first chapter. I personally found this chapter to be very enjoyable because the explanations are clear, extremely clear, and also very interesting. So we are given a vector field. It can also be called, in the problem he calls it a function. So we also call vector fields a vector valued function. Basically a function, basically a vector which is a function of the coordinates, right? So you can imagine a vector in depending on Cartesian coordinates x, y and z, but here we have a vector function which is in terms of the spherical coordinates r, theta and phi, right? And the components also of the components of the vector are also resolved. The vector is resolved along the directions r cap, theta cap and phi cap. So we are in a spherical coordinate system, and we are given this closed volume because the divergence theorem is a theorem about about closed volumes, closed surfaces, to be more precise, closed surfaces which enclose volumes, right? So let's jump into the solution of the problem. So this is the divergence theorem, that if we have a vector function v, we take the divergence of that function and integrate that divergence. So the divergence is like a derivative. It's a space derivative. So just like scalar valued functions, that ordinary functions that you study in high school mathematics, right? F of x, a function that depends on x, only one variable, a function of only one variable, that's an ordinary function. So it has a derivative. Similarly, in three-dimensional space, vector valued functions have two kinds of derivatives. One is the divergence, the other is the curl. So the divergence is just the derivative of this vector valued function v that we are given, and if we take that divergence and integrate it over a particular volume, so we are given this ice cream cone, so we integrate the divergence over all the points inside that ice cream cone. That integral becomes the left side of this equality, and the right side is the surface integral of that v. So on the left side we are integrating the divergence over the volume, but on the right side we are integrating the function itself over the surface area, over the entire surface area. So for the ice cream cone, when we perform the surface integral, we'll have to perform it over the spherical part, over the top spherical part of the ice cream cone, and also the conical part, the conical surface. So the surface can be kind of categorized, can be partitioned into two parts. There is the spherical top, where you can say that is where the ice cream is, and the conical part, that is where the cone is. So in this video we'll check this divergence theorem. We'll verify that if we calculate the left side integral and if we calculate the right hand side integral separately, they come out to the same value. We'll verify that, and we'll also while we are at it, we will look at some basics of the spherical coordinate system, how to think about the volume integral, the surface integral, how to think about the unit vectors, and so on. So here we are going to calculate the left hand side integral first, and for that we need the divergence in the spherical coordinates. So here we have the formula for the divergence in the spherical coordinates, and there is a derivation for this formula, and it is given in the appendix of the textbook, but we are not going to go into that derivation right here. We are just going to use the formula as we are given, and so in this formula the divergence itself operates on a vector. So v is a vector that we are given, but the result that it produces is a scalar. So you would notice that the right hand side is a scalar. It does not involve any reference to any unit vectors like r cap, theta cap, or phi cap. So the divergence operation starts with a vector, but it produces a scalar, and Vr, V theta, and V phi are these three components, the r cap, theta cap, and phi cap components of the vector V. Right? So all I have done in this particular step over here is I have plugged in these values of Vr, V theta, and V phi that we are given. So Vr is r square sine theta, V theta is 4r square cos theta, and V phi is r square tan theta. So we get this. So to evaluate this divergence, we have to find these three partial derivatives. So the partial derivative of r to the power 4 sine theta with respect to r would be 4r cube sine theta, and divided by r square outside, it becomes 4r sine theta. So this first term turns into 4r sine theta. The second term is a little more complicated. You can work it out, and it comes out to be this 4r cos 2 theta over sine theta. And the third term comes out to be 0, because here we are taking the partial derivative with respect to phi, but the thing that we are differentiating is independent of phi, so it becomes 0. So then we get this, and the second applying some elementary trigonometry on the second term, we get the final answer, which is 4r cos square theta by sine theta. So this particular part is not very difficult. This is something that you should have a good hold on. How to use this formula? You should be able to use, given the formula, you should be able to use this formula. This is something that you have to practice first. That once you're given the formula, how to get to the correct result, how to evaluate the divergence given the formula for the divergence in the spherical coordinates. Because in the Cartesian coordinates system, the divergence formula is very simple. It's extremely simple to remember. But in spherical coordinates, it's initially kind of difficult, kind of irritating to remember this result. And so initially you should gain confidence over how to use it, how to apply the formula, and later on when you're comfortable with using the formula, maybe because you've used it so many times, you'll naturally come to remember it, and that should come later. So we are in the process of finding this left side integral, which is the divergence of V integrated over the volume of the entire volume of the cone. So we have found the divergence, but we have come to the second step, which is how to write this elemental volume d tau. So d tau denotes an infinitely small volume around a point. So if we were in if we were using the Cartesian coordinate system x, y, z, we would take the elemental volume would be extremely simple, dx, dy, dz. So I would explain over here how we can get the elemental volume in the spherical coordinates also in a very simple manner, and you would appreciate that it's a very simple process, right? So first we will familiarize ourselves, we will make ourselves comfortable with what the spherical system is, what the spherical coordinate system is. So if we are at a particular point, so this is our point, so where my pen is currently, this is my point, and this is the origin. This is the x-axis towards the right side, the z-axis goes upwards, and the y-axis goes right into the screen, right? So y-axis goes perpendicular to the screen, into the screen, right? So these are my axes, and this is the origin where I am right now, and this is my point. This is a general point which is denoted by the coordinates r, theta and phi. So r is obviously the distance, r is the distance of the point from the origin. Theta is, if I join this point to the origin, I get the position vector, right? And the position vector is a vector which has its head at this point and its tail at the origin. So the position vector of a point is a vector which points from the origin to that point. So if the position vector is in this direction, it makes a particular angle with the z-axis. That angle can be 0, that angle can be pi by 2, can be pi by 3, it can take many values, right? So for example, if that point is in the xy plane, the position vector of that point will make a 90 degrees angle, it will make pi by 2 angle with the z-axis, and in that case theta will be equal to pi by 2. So for all points on the xy plane, the theta coordinate is pi by 2, is 90 degrees, right? So the position vector, the angle that the position vector makes with the z-axis, with the z-axis, is theta, is what we call theta. So if I take a point on the z-axis, for example, that theta will be 0. So for all points on the z-axis, their theta coordinate is 0. I think that makes sense. What about phi? Phi is, so if this position vector, if I take the projection of this position vector, so if I take the shadow, if my position vector is this line which points from the origin to this point, if I take its shadow on the xy plane, I get this line, I get this small line, right? So this shadow on the xy plane, the angle that it makes with the x-axis is my phi, right? Is my phi. So and phi is obviously counted counterclockwise, just like, so phi is the same angle, it's called the azimuthal angle. It's the same angle that we use in two-dimensional polar coordinates, right? In two-dimensional polar coordinates, we typically use the symbols s and phi, right? Sometimes we use r and phi as well. But to differentiate this r, the r of the spherical system from the r of the two-dimensional polar system, I'll call that s. So in the two-dimensional polar system, the angle phi is exactly the same angle phi that we have in the spherical system. They are the same, and that is the angle made by the by the projection of, in the spherical system, it's the angle made by the projection of the position vector onto the xy plane. The projection, first take the projection, and the angle made by the projection with the x-axis is phi. So for example, if I have a point on the x-axis, phi will be 0. If I have a point on the positive y-axis, phi will be pi by 2. If I have a point on between the in the second quadrant, in this part, in the second quadrant, phi will be between 90 degrees and 180 degrees, between pi by 2 and pi. So it is good to have some kind of intuition, for it, and to check whether you can write the coordinates of a particular point, of different kinds of points in the spherical system, right? And what are the position vectors? R cap, phi cap, and theta cap. So if I am at this point, so this is very important, this is very interesting manner in which you can very easily and clearly understand the position vectors. So in Cartesian coordinates, x, y, z, x cap, y cap, and z cap, the unit vectors are the directions, point in the directions in which x cap points in the direction in which x increases, but y and z remain constant. Right? So you can start with the two-dimensional system because we have a good intuition developed for the two-dimensional system. In the two-dimensional system, x cap is the direction, such that if I move in that direction, if I move in the x cap direction, my x coordinate increases and my y coordinate remains constant. Right? So there is an orthogonality as well. There is the coordinates, the two coordinates are perpendicular. You know, what I mean by that, that it is possible for us to increase one of them without changing the other. Right? So it is possible, they are independent in a sense that they can be changed independently of each other. Right? Or we can call that they're orthogonal. That's a more technical word, but it essentially means the same in this context. So in the three-dimensional Cartesian system x, y, z, x cap, y cap, and z cap are the directions in which x cap is the direction in which x increases, but y and z remain constant. Y cap is the direction in which y increases, x and z remain constant, and z cap is the direction in which z increases, but x and y remain constant. So similarly, exactly the same logic applies here. So if I start from this point, in which direction should I move such that my phi increases? So let's start with phi. So it's quite obvious that if I move in this direction, if I go around the circle that I've drawn here, if I go, so I'm moving in a plane which is parallel to the xy plane. So if I'm starting at a general point, this point that I've drawn is a general point, and from this general point, if I start moving in a plane, in a circle around the z-axis, if I start moving in a circle around the z-axis, and that circle is parallel to the xy plane, I increase or decrease phi. So if I move in the counterclockwise direction, I increase phi. If I move in the clockwise direction, I decrease phi. So it's also quite obvious that if phi cap is the direction in which phi increases, minus phi cap would be the direction in which phi decreases. So phi cap would point exactly the opposite direction, because if I move clockwise, phi decreases. Right? So by the way, at the point that I've taken over here, phi is quite a large angle, because I've come all the way around into the fourth quadrant. So my angle is between 270 degrees and 360 degrees. And of course phi repeats after one cycle is complete. So phi only takes values between 0 and 2 pi. So if I start moving counterclockwise from here and I reach the x-axis, I start over. I reach phi becomes 2 pi, but that 2 pi it can be taken as 0 as well. So I start over from 0. Right? So phi cap is this direction, it's obvious. R cap is obviously if I start moving away from the origin, because R is the distance from the origin. So to increase R, I have to move right away, from the origin. I move exactly away from the origin, right? And also checking that, so let's come back to phi cap. So if I increase phi, if I move in the phi cap direction, does my theta change? So as long as I'm on this circle, my theta does not change, right? Because the angle made by this line that joins the point to the origin makes a constant angle theta with the z-axis. This angle theta remains constant. I'm just moving on this circle. Anywhere I'm on this circle, the theta is the same, and the r is the same. I'm at the same distance from the origin, by the way. So we are quite sure now that this must be the direction of phi cap. That if I move in this direction, if I move a small distance in this direction, my phi cap, my phi changes, but my r and theta remain constant. Coming to r cap, if I move in this particular direction, if I move right away from the origin, right, but my theta will remain constant because I'm still moving on this same line, and this line makes the same angle, makes a constant angle theta. The line, if the line is the same, the angle that it makes with the z-axis also remains the same. That's quite logical. And if I move in the r cap direction, theta remains constant, and phi also remains constant, because this line, I might be moving a further distance away, but this shadow that will that I'll have, the shadow of the position vector on the xy plane, will increase in length somewhat. So of course you might think that I'm going too fast, but you can pause the video and you can think about these things, because thinking about them on your own will really, you know, make you appreciate and make you learn. So r cap is the direction in which, if I move in that direction, r increases, but phi and theta remain constant. So you can have a similar discussion for theta cap. If I increase theta, so I've drawn this curved line over here to denote the path. So if I were at this point, and the distance of this point from the origin is also, let's say, small r. So if I now start rotating my position vector in this particular direction, right, such that the length of the position vector remains constant and phi also remains constant, but theta increases. So this is the direction. So if I start if I start rotating my position vector in this direction, right away from the z-axis. So because theta is the angle made by the position vector with the z-axis, if I start tilting away, exactly away from the z-axis, my theta increases, but because this shadow, again, the shadow remains in the same place, right? The length of the shadow might change, but the direction in which the shadow points remains the same, and phi remains the same, and r of course remains the same, because the position vector has the same length. The length is not changing. So this is essentially what the spherical coordinate system behaves like. R, theta and phi are orthogonal coordinates, that any one of them can be changed at any point, starting from any point in the three-dimensional space. Any one of the coordinates can be changed while keeping the other two constant. This is very important, and this is a very important feature of the three-dimensional system, of the spherical coordinate system. So you can test your intuition about what we just talked about, how the coordinates r, theta and phi behave, and how they are related to the x, y, z system. I think you should do this exercise on your own. You can pause the video over here, and you should test all these results. All these results are true, and they are just here to, you know, make yourself more confident about your own understanding of the spherical coordinate system. So I'll move on, and what we were trying to do was write the elemental volume, the infinitely small volume that we get in the spherical system. If we are at a point r, theta, phi. So how to get that elemental volume is very simple. That if I move very small amounts one by one, so if I move a very small amount, so how do you form a rectangle, for example, in two-dimensional space? How do you form an elemental surface area in two-dimensional space? It is dx times dy. So you form a small rectangle, or square, you can call it a square, but in general it's a rectangle. That you move a very small distance in one direction, you move a small distance in the other direction, and because the two directions are perpendicular, you get a rectangle, and the area is just the multiplication of those two dimensions that you moved. You moved a distance dx in the x direction, you moved a distance dy in the y direction, and therefore you get an area which is dx times dy, right? So similarly, in three-dimensional space, you also move in a third dimension, which is dz. So you get a volume dx, dy, dz, and you get a cuboid, right? In the spherical system as well, because you're So a very important difference about the spherical system, which is very different from the Cartesian system, is that r cap, theta cap, and phi cap are directions which are not the same everywhere. So if I look at this diagram again, so if I am at the z-axis, for example, r cap, if I am at this point on the z-axis, r cap points straight upwards. But if I am at this point, r cap points in a different direction. If I am at the z-axis, theta cap points perpendicular to the z-axis. But if I am at this point, theta cap is no longer perpendicular to z-axis. So r cap, theta cap, phi cap are different at different points in the three-dimensional space, right? This is a very, very important difference from the Cartesian system, and we need to be careful about this, because in the Cartesian system, x, y, and z cap, the three directions, are constant directions. Wherever we are, x cap always points in the same direction, and so on. So because of this difference, you might argue that if I move very small distance, if I move a particular distance in the r cap direction, if I move a particular distance in the theta cap direction, and if I move a particular distance in the phi cap direction, very small distances, I will not exactly get a cuboid. I will get something like a curved surface, a solid which has curved surfaces, because the coordinate system itself is curved, right? So if I move a very small distance in the phi cap direction, for example, I will get an arc of a circle, right? And if I move a very small distance in the theta cap direction, I will also get an arc of a circle. But because these distances are extremely small, the figure that they will form can be considered a cuboid. It is a cuboid in the limit where the distances moved are almost zero. They are very, very small, right? So to generate this elemental volume, all I have to do is move very small distances in these three directions, measure those distances. So my question is, if I move very small distances in the r cap, theta cap, and phi cap directions, what are those distances? What is the measure of those distances in terms of the small changes in the coordinates? The small change in r, which is dr, the small change in theta, which is d theta, and the small change in phi, which is d phi, right? So my question is, what are those small distances that I get when I move in these three directions? So in the r cap direction, it's very simple that the distance that I move will be dr. It will be the very small change in r, because when I'm moving in the r cap direction, all I'm doing is I'm changing the distance. I'm changing r, right? That is the definition of r cap. That if you move in the r cap direction, r increases. In the theta direction, you are just rotating the position vector away from the z-axis. So the angle already made by the position vector with the z-axis is theta. So if I increase that angle by a small amount d theta, all I do is I move in a circular arc, and that the length of that circular arc is r d theta. So that's very simple. And the phi cap direction is a little more complicated, but it's quite simple. So if I move in the theta cap direction, again I'm moving in a circular arc, but now the radius of that circle is this length, and this length is from this triangle just r sine theta. So r sine theta is the radius of the circle, and I'm moving in that circle, and the phi angle changes by a small amount d phi. So what is the small length of that arc? What is the arc length that I move? It is r sine theta d phi, right? So these three lengths are the lengths that these are very important concepts, that if I move very small lengths in these three directions, I get these three these are the lengths that I get in terms of the small changes in r, theta, and phi. So these are the elemental you can say the elemental steps, elemental lengths that I move in the three directions. And to get the volume of that figure that I get a cuboid. Which has one dimension is dr, one dimension is r d theta, and in the third dimension is r sine theta d phi. So the volume that I create, if I make small changes starting from any point, if I make small changes in r, theta, and phi, I get a figure, a cuboid, which has these three dimensions, and the volume of that figure is just the multiplication, because it's a cuboid. It's just the multiplication of those three lengths. So I think this is a good point to stop for this particular part of the video, and the second part of my video will finish the problem. But I'm stopping here because this is a very important juncture, because we have really discussed the spherical coordinate system and the elemental volume in quite a lot of detail, and to understand this and to digest this information is absolutely essential to move on to the second step, because there was a lot of density of material in this part, and it is good to go over that and to develop your intuition and to practice testing your intuition using this slide, and to also understand how these three lengths come about and why multiplying these three lengths gives us the elemental volume. So see you in part 2.